Okay, on this video we are going to see the applications of differential equations, and the first model we are going to cover is the growing or decay model. Alright, let's start with the population model, which was one of the first models of differential equations. So an economist in England, he realized that the population rate, the speed or velocity that the people rose in a city, it was proportional to the size of the population. Okay, so he realizes something like I'm going to propose here. So let's assume that in Wimilpan, close to Querétaro, there is a little village where there are 2,000 people living in that little village. In compared to Querétaro, that today has 1.5 million people, so obviously Querétaro is much bigger than Wimilpan. But what about the Mexico City? Mexico City, it has over 21 million people. So the question I'm going to ask here is, which of the three populations is going to grow faster? And when I say faster, I'm meaning speed. So obviously the city that is growing faster is the Mexico City, while the population in Wimilpan is growing slower because it is proportional to the current population available for making new babies or new people. Alright, so that is the model. So as you can see here, the bigger the population, the faster it's going to grow. The smaller the population, the slower. And pay attention when I say faster and slower, because that means speed, velocity. And in terms of derivatives, the derivative is actually the velocity, the rate. So this English guy said, okay, the rate of the people growing in a city is proportional to the current population at any given time. Okay, and at any time of the current population. And I'm going to make here the rate. The rate is actually the velocity, the speed, the rate of the people growing. So that means that the rate of the population growing, I'm going to erase this part of this example, because I'm going to make the model in the differential equation shape. Okay, so the rate of the people growing, because P of t is the population at any time t, then the rate of the population growing is actually the derivative of the population with respect to the time, according to the time. Alright, so this means it is like 30 persons per day, for example. Alright. That will be for a small village, maybe not Querétaro, but for example in Wimilpan will be like 3 persons per day. But in Mexico City it will be like 3,000 persons per day. So here the concept is velocity. Persons, the rate is persons per day, or persons per month, or persons per second. That is going to be more difficult, but let's assume it is just the time. Okay, now the rate of the people growing, this rate, this velocity, is proportional to the current population. Now, when I say proportional, the concept of proportional is that things are not equal. They are proportional to something. For example, let me give you one example here. Let's say that currently today the exchange of pesos and dollars, for example. Alright, let's say that today we have like 22 pesos is equal to $1, $1 US. So the rate, the proportionality is this 1 over 22 if you make certain conversion of 2 times the dollars. Alright, so this is a proportionality. Alright. So another proportionality, and that proportionality is not always constant. It's different. It's just that the proportionality, it means that something else is not always equal to another thing is just proportional. If something increases, the other also increases, but in the same proportionality. Maybe twice, or maybe the same, which will be equal, or twice, or 3 times. So if this one grows 1, the other grows 3 times. But then if this is grows 2, then the other is going to grow 6 times, 6 units. So that is the proportionality. All right. So the concept here is that the rate of the people is proportional to the current population. So that means that it's not equal, it is proportionality. And the proportionality is K times P of T. And as you can see here, this is the differential equation. And the differential equation happens to be a variable separable differential equation that we can solve. Okay, so let's solve it. Here is the proportionality. This K is the proportionality. This proportionality K could be 2, could be 0.5, or could be different. Now, this proportionality depends on the environment. Okay, what do I mean with environment? Okay, that proportionality. Let's say that in Europe there is a little village in the same size as Wimilpan, but the political and the geographic and the economic situation is different from a village the same in Europe and then a village here in Mexico. So that is the proportionality. So a different the same population in different places they are going to have different conditions. So that proportionality is going to be different. All right. So this environment depends on mortality and birth rate or conditions that are specific for that environment. All right, but what I'm carrying here right now is how to solve this differential equation. So this is a variable separable differential equation, P differential of P of T over P of T equal to just K differential of T. So as you can see here, only P, and here is just T. And we already know how to solve this differential equation. You take the integrals on both sides. So on the left side, you have the natural logarithm of P of T, and that is equal to just Kt plus the constant. Don't forget the constant. And let's clear the population, which is what we trying to model. So if you take the exponentials on both sides, so what you are going to get is this and this cancel, so you are going to get the P of T equal to the exponential of Kt plus the constant, but I'm going to write like this, exponential of the constant, because the power they sum together. Now the exponential of a constant is still a constant, so P of T is equal to the constant exponential of Kt. Now, have you heard this term that the population is growing exponentially? So that is the reason. Here, the model of the population growing is an exponential, all right? So, engineers, we are going to solve a problem of growing population using already the model. You don't have to do this every time. If you take the model, then you can apply it, all right? Now, one important thing here, if it is growing means that K is positive. If it is a decay, then means that the K is negative, all right? Okay, so why is that positive? Well, the derivative here, the derivative is proportional to the population. The population is not negative. It should be only positive because there is no minus 3 persons, all right? But here, what gives the derivative, the sign is the proportionality. Now, imagine if this is negative. Well, if this is positive, then the derivative is increasing. Then the slope is positive, is growing, all right? Now, if it is negative, that means that the slope is negative, so it is decaying. Now, how can a population decay? Let me give you one example. The population doesn't mean it has to be persons, humans. It could be microbes, or it could be organisms. It could be, for example, those animals in extinction, in danger of extinction, where the population is actually decaying. For example, the fishes in the oceans. All right, so the population could decrease. So that is why the proportionality decay, if it is positive, then it is growing. If it is negative, then it is decaying. It's going down. All right. So here, the plot for each one of them is going to be, in the growing, is going to be something like this, or something like this, decaying. So this is with K positive, and this with K negative. Okay, so that will depend on the conditions of the problem. But this is the model, very important. This is the model that we are going to use. On the next video, we are going to solve a problem of growing or decaying population. All right, see you in the next video.